well. So the first speaker is Ruiting Ma.
Yes. Can you see my screen?
I'm going to talk about open time hadrons. So please start.
Okay, thank you. Is it in the full screen mode? Oh,
yes.
Oh, okay, thank you. Hello everyone. Today I will give the report about the open charm exotic hadrons, the X2900 and X2900, on behalf of the RCP collaboration. And first, I will give a brief review of the B2DDH decays and then introduce the model independent analysis and also the amplitude analysis on the B plus to D plus D minus K plus decay channel. And finally, I will give a conclusion and the next step of the B2DDH analysis in the RCP collaboration. So first, the B2DDH decays. Well, we know that the B2DDH decays, it involves a huge family of topologically similar decays. Here, B could stand for B0, B plus, B sub I, lambda B, and D includes D star sub I, lambda C, and the hadrons here are the light hadrons like pi on K on phi lambda X, etc. So we could imagine that there would be many intermediate states, such as the charmonium states, the high excited destabilized lambda sigma C states, and also the possible exalted states include in the three-body decays. So the B2DDH decays, they are powerful exclusive decays for the hadron spectroscopy studies. So up to the years before this X2900 analysis was published, there have been several B2DDH branching functions. They have been measurement, but only the amplitude analysis for 2 decays have been performed. One from Bell in 2008 and another one from Babar in 2015. And the bottom plot, it shows the result from Babar analysis. They have about 400 to 800 signals with about 40 purities. So we could expect that this result could be improved by the RCP collaboration, since we have large statistics and high vertex and also momentum resolutions to surprise combinatorial background. And this plot is the structures of RCP detectors, but I would like to skip the details to save time. And up to now, there are 2 published B2DDH branching function measurements in the RCP collaboration. It's the measurement of the branching functions for the B2D star decay decays and the first observation of the decay B2D0 D0 bar K pi. And the bottom plot shows some results from the first analysis. We could see that all these channels, they have high statistics with high purities, so they could be ideal B2DDH data samples for the amplitude analysis. So first analysis is a model independent analysis on the B2D plus D minus K plus decay. Well, why we choose this channel as the first B2DDH amplitude analysis in the RCP? First, it is because it's haven't been explored yet, and the second reason is because, well, in this channel, only the charmonium and charmonium-like states are expected in the 3-body case. It means that it's more easier to build the fitting model for the amplitude analysis. And for the data set, we use the full RCP round 1 and round 2 PP collision data set. And signal candidate is constructed through this channel. And we also apply the uniform BDT with topological and PID variables to surprise the combinatorial background. And finally, we got 1,260 candidates within the B plus minus window with about 99.5% purities. So it's indeed a data set with high statistics and high purities. And We then have a brief look at on the Dulles plot. And in the DD spectrum, we could see that there are two narrow peaks. On the left side, they may contribute by the psi 3770 and also the Cassie2 3930. But there is also a obvious peak on the D minus K plus spectrum around 2.9 GeV. So whether it is a new exotic state or it's just some reflection from D plus D minus resonance, we build a model independent analysis to test light. We first decompose the helicity angle of the D plus D minus according to the basis of the Legendre polynomial at here, and then divide the mass spectrum of the D plus D minus into slants. Here, the coefficient of being J weighted by order K Legendre polynomial can be expressed at here. And the distributions of the Legendre weighted total amplitude, YK, with K equal to 2J, it could account for the contributions of the charmonium resonance with the spin up to J max. So this picture shows the distributions of the unnormalized moments with K up to 8. And we can see that the YK with K larger than 4, they are almost flat, means the contributions from the charmonium state with spin larger than 2 would be limited. So to test the significance of the potential new resonance in decay spectrum, we choose to generate phase-space Monte Carlo samples and weighted each Monte Carlo candidate through this function.
Eugenione, come va?
Oh, sorry?
Bene, volevo sapere se stai mangiando.
Oh, okay, let me go ahead. So here's the YKJ is the value of the order K Legendre polynomial coefficient in bin J, shown in the last picture. So we then project the weighted Monte Carlo samples to the mass spectrum of the D minus K plus and also the D plus K plus to check if it can describe the distributions on these two Ewald mass distributions. And the results are shown in the right plot. With the high order polynomial, here the Kmax is equal to 29. We could see that the distributions of the D minus K plus Ewald mass could be well described. But if we limit the Kmax to 4, there would be clear deviations on the D minus K plus mass spectrum around 2.9 GeV. And the significance of this disagreement is estimated to be 3.9 sigma with K equal to 4 and 3.7 sigma with K max equal to 6 by using the tested statistic. So it's indicated a new exotic, or at least a new exotic charm string resonance at here. So we then perform a model-dependent amplitude analysis on this decays to extract the parameters of the potential exotic resonance. The amplitude analysis is performed based on LoRa++ Dulles plot filter. The likelihood in the fit is it contains some Gaussian constraints on the mass and weight of some well-known harmonium states, and also the signal model and the background model. Here, the signal PDF is defined as a normalization factor times the efficiency part times the square of the total signal amplitude. And signal amplitude is sum over all the resonant amplitude, while each resonant amplitude it includes the Breit-Wigner functions, angular factor, and two barrier factors for the first and second order decays. Here, the efficiency map in the amplitude analysis is extracted from the simulated examples with data-driven method to correct the data Monte Carlo differences. And the round 1 and round 2 data set, they are fitted simultaneously with corresponding efficiency map. Here shows round 2 efficiency, relatively efficiency map as an example. And for the background modeling, we use B plus sideband samples and relaxing the BDT requirement to increase the sample size. And we also apply the kernel estimation procedures to reduce the statistic fluctuations. So for the fitting model, from the model independent analysis, we know that there are possible D minus K plus resonance contributions in this decay. But in the first step, we still try to fit the data distributions with the model content only harmonium resonance. And since only harmonium states with a natural spin parity, they are allowed to decay into D plus, D minus final state. We list all the possible harmonium resonance in PDG at that time and here. So for the fitting procedures, first, we always include the Psi 3770 and the KC2 3930 in the fitting model because this band they are obvious in the dilute plot. And then we test the other harmonium components in the table to see if it can significantly reduce the low likelihood. And we finally choose to include these 4 Psi states and constraints these mice and weights with to the PDG value with Gaussian constraints. And we also include an additional KC0 3930 states to the fit model to improve the fitting quality. And we also test a series of non-resonant line shape during the fitting. And finally, this page shows the fitting results with the basic fitting model with 4 Psi state and 2 KCG states. Here we can see that the mass spectrum of the D plus D minus and D plus K plus could be well described by the fit result, but for the D minus K plus distributions, there is still a large deviations around 2.9 GeV. It is consistent with conclusion in the model independent analysis. So we then try to edit the D minus K plus resonance to improve the descriptions on its spectrum. We try to edit either 1 or 2 exalted resonance with different spin parity assumptions, and the result with 1 0 plus and also 1 minus D minus K plus resonance, it could give the biased fitting qualities, and the mass and weight of the 2 resonances are listed at here. We then calculated the significance of the 2 exotic resonance. It's determined by the particular experiments. We generated 1,000 toy Monte Carlo samples from the fit result without the decay components, and then fitted each toy Monte Carlo samples with and without the decay resonance, and calculated the dirt likelihood. And the distributions of the dirt likelihood are shown in this page. We can see that it's far from the dirt likelihood in data. So the significance is overwhelming.
So you have 3 minutes. Yeah.
Okay, yes, so, thank you. The significance is overwhelming larger than 5 sigma. So for the tetraquark candidates with 4 different flavors, we know that in 2016, the D0 collaboration, they report evidence of the B sub R pi plus resonance called X5568, but unfortunately, it isn't confirmed by the other experiment. So if the exist of the X0 2900 and X1 2900, they could be confirmed in the other B2DDK channels or the other experiments. They could become the first confirmed observations of the tetraquark states with 4 different flavors. And during the amplitude analysis, we also found that it's necessary to include both the spin 1 and spin 2 KCG components in the exists KC2 3930 mass region to describe the mice and also angular distributions of the dataset in the KC2 slice. The mean short mice of the KC0 states is consistent with the KC2, but the weight is more narrow. And for the Cassie states in the results, there are still some remaining questions like why the Cassie2 mice in this analysis is not consistent with the inclusive studies in the RCP collaboration, and why we didn't see the Cassie03860 components in these decay channels, where we need more statistics to clarify that. So conclusion, we use a model independent method to study the intermediate state in the B+ to D+ D- K+ decays, and the results indicated some possible resonance on the D- K+ spectrum. So we then performed an amplitude analysis on the same data set, and two exotic D- K+ resonance with spin 0 and spin 1 observed. We also discovered the distributions from spin 0 and spin 2 Cassie components in the region of the existing Cassie2 3930 state. So in the next step, for the B2 DDH analysis in the RCP collaboration, there are now several ongoing B2 DDH analyses with round 1 and round 2 dataset. And some of them, they are aimed to publish within 1 or 2 years. And we know that the RCP round 3 data will start in this year. And with 10 times statistics, we could perform detailed analysis on this B+ to D+ D- K+ channel to understand the above some problems, and also try to explore more potential B2 DDH channels in future. That's all. Thank you.
Okay, thank you very much. Is there any questions? Okay, I don't see any. Oh, Eulogio has a question, so please.
Yes,
Eulogio.
Thank you, Raquel. I'm sorry I asked this question again, but by looking at your transparencies, I realize, that you are doing, correct me if I'm wrong, you are doing a partial wave analysis already, but I think only in the KD, right? But not in the DD. Now I say that because, if it was possible to do also the partial wave analysis on the DDE, D+, D-, separate the S wave, that would be of great help. Sasa is there in the audience, and it would be very nice, to see what happens, because, she, with Lattice and many other people, doing effective theories, predicted that there should be a bound state of DD bar, and then that should be seen somehow with an enhancement around threshold. So I don't know what you have something to say about that.
Oh, you mean for the DD with same?
Correct, about this, yeah, D+, D-, yeah.
Oh, well, how to say, if you, if I understand correctly, you means you want to search for the
zero, L = 0, S wave for D+, D-, separate that part. The S wave or D+, D-, that would be of great help.
D+, D- in this case?
In S wave, separate that in S wave.
How to say, maybe we could try to explore that with the round 3 newest site.
So,
yes.
So far you see, the decay of the GC0, you see the decay of a, of one vector. You see the decay of one vector into D+, D-. That's why I say one should separate, right? One should separate the S wave to see if there is an enhancement close to threshold.
Oh, yes. Well, for now, it's maybe the limited of the statistics we can. This is what we can.
Right. You see a peak there, right? You see a peak which comes from the 3000. The D+, D- from the 3770, which is a vector. Vector going to D+, D- in P wave. That's why I say if one could separate the S wave from there in partial wave analysis, then that would be great. Yeah, we would be happy. Sasa would be very happy about.
Okay. Yes. Thank you. Maybe I can discuss with the major authors to see whether he could do that. Yes.
Good.
Sorry,
Thank you.
just to point out.
Okay, I think Fenkun has another question, so please.
Yes, thank you. Thanks for the very nice talk. And actually, my question is related to Alohi's ones. Yeah, I think I'm sorry that I have asked this the same question to some other speakers of RCB before, but I do not remember really the answer. So the point is that now you see in D plus D minus spectrum, you see the peak of 3770 is not the highest one, right? Is lower than the next one. This would be 3930, right?
Mm-hmm.
But if I remember, I checked some old data by either Bell or Barbar, by which one I cannot remember. They observed the same three-body B meson decays, and their spectrum looks different. Of course, they don't have that high statistics, and also from theoretical point of view, one would expect that on for instance, because of the V minus A current, the CC bar will be more easily produced in vector and actual vector quantum numbers. And in this case, I would see related to Alohi's request, the scalar might not be that copiously produced in comparison with the psi, for instance, 3770. And just don't know the answer or from your side why this. Have you compared to the previous data, and are they really consistent with the other experiments?
Well, sorry, I didn't do that. And for my understanding, why this peak is lower than the second one, maybe because, well, maybe you can check this. It's oh, I see. So it's oh, sorry for that. Well, I have I also I didn't check the other experiments, so maybe I can discuss with them later. So
yeah,
well, I'm not sure about the answer. Yeah.
Or anybody in the audience know the answer?
No. No.
I mean,
because it's a bit surprising that psi 3770 is lower than the next one.
Well, I mean, the data are very clean, and as a speaker commented, acceptances are not necessarily the same. So comparing cross spectra without efficiency corrections, it's not the right way to compare.
Yeah, sure. And that's correct.
Which reminds me, sorry to interrupt, that we will thank very much if we give the data corrected already by efficiency, for efficiency. That would be very helpful for us also.
No, but you see, the problem is efficiency is not one-dimensional. So efficiency is many-dimensional to do it correctly.
Yeah, but I mean, you can take that into account, I mean, for any projection. Yeah, I mean, that's no problem. Because I mean, it's very unlikely that any theoretician will go to the Dulles plot, you know. I mean, we always look at invariant masses, as many as you want to give us in all the different channels. But I mean, certainly you can do, I mean, the efficiency corrected, I mean, projections also in each one of the pair invariant mass of each pair. That would be very helpful. I mean, you would really thank it very much.
And also, can you point that out? Which line in the upper left figure corresponds to 3930 with scalar quantum numbers? I mean, how much of this very, very high peak comes from the scalar? How much does it come from the tensor?
Oh, well, maybe I need to check the papers for the fractions of the two.
Yeah, it's not clear from this small figure.
Okay, I think maybe we can leave
Yeah.
these questions for the discussion session and we can
Thank
go
you.
ahead with the next talk.